Welcome to the Explainer. Today, we're diving into something that is truly shaking up the AI landscape, DeepSeek V4. We are going to unpack exactly how this brand new architecture brings highly efficient, 1 million token context intelligence straight to the open source community. If you've been following the AI space, you know that scaling up to handle massive amounts of text without running out of memory is basically the final frontier. Well, DeepSeek V4 doesn't just push that boundary, it completely redesigns how an AI model reads and remembers.
Okay, let's dive right into this. DeepSeek, the team with the iconic whale logo, is undeniably becoming a massive player in the AI game. And what makes this particular release so incredibly exciting, and frankly, why people are calling it one of the biggest updates since GPT-4, is the sheer scale. They are offering a massive 1 million token context window with top-tier performance on reasoning and coding, and they're doing all of this at an absolute fraction of the usual computational cost.
So how exactly did they pull this off? To understand that, we have to look at the fundamental question that drove their engineering. What if we just stopped treating every single token equally? You see, the big headache with current AI models is that as your input gets longer, everything gets way more expensive. Not just a little bit, but quadratically expensive. The traditional attention mechanism basically forces the model to give every single word equal computational weight, which creates this massive bottleneck the second you try to scale up.
Well, DeepSeek looked at that quadratic explosion and completely re-engineered their approach. Think about it like this. Imagine you're reading a massive textbook. Instead of constantly rereading every single page to remember what's going on, you just write these highly compressed, brilliant little summaries in the margins as you go. Then later on, you only reference those summaries. DeepSeek compresses information as it reads, relying on those dense summaries most of the time, and only zooming into the exact granular details when it absolutely needs to.
So here is our roadmap for today's explainer. 1. The context bottleneck. 2. Compressing attention with CSA and HCA. 3. Making massive models efficient. 4. Pro versus flash models. And 5. The system-level shift.
All right, kicking things off with Section 1, the context bottleneck, and the quadratic cost of long context. Here's the deal. As your input context gets longer, the cost doesn't just go up on a straight line. It literally explodes quadratically. We all know that reasoning models get great results by taking more time to think, right? But forcing full attention over every single token is just financially and computationally brutal. And the real villain here? The KV cache. You simply run out of memory to store all those contextual states. Just throwing more compute power at the problem isn't going to cut it anymore. You have to fix the actual memory architecture.
Let's move to Section 2 and see how this builds. Compressing attention and their hybrid approach to million token contexts. Now this is where the magic actually happens. The model alternates between two entirely new attention mechanisms, CSA and HCA. On the left, we've got Compressed Sparse Attention, or CSA. This one is highly selective, very fine-grained. It compresses groups of nearby tokens into meaningful chunks. And we're not talking about simple averaging here, this is learned compression. Then it uses a top K selector to score them, basically ignoring the noise and attending only to the most relevant chunks. But over on the right is heavily compressed attention, or HCA. This is aggressive and it's global. It collapses massive sections of tokens into single dense representations, and then runs dense attention over that tiny compressed set. By alternating between CSA for those fine details and HCA for global scalability, they make that million token context totally feasible.
Now what's really interesting about this is how it affects memory. Because CSA and HCA compress tokens at totally different rates, the KV cache becomes heterogeneous, meaning it's full of different shapes and sizes. To handle that chaos, they split the cache. They use a state cache for the uncompressed, recent tokens, kind of like a sliding window, and a block cache for the compressed CSA and HCA tokens. They co-design this memory layout directly with their custom hardware kernels, padding the blocks to align perfectly. It's honestly just a masterpiece of engineering.
Moving straight into Section 3, making massive models efficient. Let's look at the innovations under the hood. DeepSeek uses a mixture of experts, or MOE architecture. Normally, storing a huge number of expert weights puts an incredible strain on GPU memory and network bandwidth. But check out their custom MegaMOE kernel. They split the experts into these tiny waves. As soon as wave 1 finishes its network communication, it immediately starts computing, right while wave 2 starts its communication. They are literally hiding the network latency completely beneath the computation. It's so clever.
And to squeeze out even more efficiency, they upgraded their underlying infrastructure in 3 massive ways. First up, FP4 quantization. They shrink those giant expert weights down to an incredibly low-precision format. That drastically reduces GPU memory consumption and actually speeds up inference. Second, they use the Munchuan optimizer during training, which gives them much faster convergence and keeps things stable. And third, MHC, manifold constrained hyperconnections. This replaces standard residual connections. By mathematically constraining the signal, they prevent the data from exploding or vanishing as it travels through these super deep neural networks.
Next up, Section 4, Pro versus Flash models. 2 models, 1 architecture. So DeepSeek released a preview of 2 separate models built on this exact same hybrid architecture. And yep, both of them natively support that 1 million token context length. First is DeepSeek V4 Pro. It is a total behemoth, 1.6 trillion total parameters. But because it's an MOE model, only 49 billion parameters are actually active for any given token, which makes it top tier for really complex reasoning tasks. But look at the Flash model. It has 284 billion total parameters with only 13 billion active. Yet the data shows the smaller Flash model actually outperforms the massive baseline of their previous V3.2 model. This is a monumental proof point. A fundamentally better, more efficient architecture can flat out beat sheer brute force model size.
Which brings us to Section 5, the system-level shift, and how they are redefining the state-of-the-art.
So what does all this crazy architectural innovation actually mean for real-world efficiency? 27%. In a 1 million token context setting, the massive DeepSeek V4 Pro model requires only 27% of the single token inference flops compared to its predecessor. It is literally doing fundamentally less math to achieve better results.
And the crucial point here is 10%. They slashed the KV cache size down to an unbelievable 10% of the V3.2 baseline. Like the source material states, this isn't just some incremental gain. This is a massive system-level shift. It means 1 million tokens isn't just some theoretical maximum for a lab anymore. It's something you can actually, routinely, and affordably support in production.
And here is the ultimate proof. On the left side, you've got DeepSeek V4 Pro Max going toe-to-toe with frontier, closed-source giants like Gemini and Claude on deep knowledge and reasoning benchmarks. It's fiercely competitive, but the right side is the real story. Look at the blue lines for V4 Pro and Flash. The computational cost and accumulated cache essentially flatline at the bottom of the graph, while the dotted line of the old architecture just skyrockets out of control. It delivers state-of-the-art capability with absolutely plunging computational costs. By completely solving the quadratic scaling problem of attention, DeepSeek V4 hasn't just built a better model. They've unlocked a totally new paradigm for the entire open-source community. The memory barrier is officially broken. So I'll leave you with this. With ultra-long context now highly efficient, open source, and practically free of the old memory constraints, what will you build with 1 million tokens? Thanks for joining me on this explainer. Keep learning, and I'll catch you on the next one.